In this video, we are going to focus on how we can represent decimal numbers in two's complement form. Okay, so we studied about sign magnitude and one's complement form. To study two's complement form, you have to have a basic understanding on one's complement. So one's complement is fairly simple. Let's say you have, I will attach the link obviously, but I just want to go through some important things. If it's a positive number, okay, let's say we are talking about the 8 bits representation. There are multiple bits representation, obviously, but we have to focus on 8 bits representation. So if you have 8 bits, the first bit is allocated for the sign, okay, even in one's complement. Only the other 7 bits are used for representing the magnitude of the decimal number. For example, if you have a positive number, let's say if you have positive 79, positive 79 in binary can be given as 64, no 32, no 16, 8, 4, 2, and 1. So this is the 79 in base 2. Okay. So since this is a positive number, you have to put a 0 here, and you can fill out the other numbers. This is the ones complement form. Okay. This is the ones complement form of 79 to the base 10. Okay. This is the ones complement form. And if you want to find negative 79, what you have to do is you just have to find the inverse. Okay, you just have to find the inverse. So it will be 1, 0, 1, 1, 0, 0, 0, 0. Okay, so you're converting the bits inverse. Okay, so you're writing down the inverse of the bits. Okay, so this is what one's complement is. So what are we going to do in two's complement? Well, in two's complement, if we are talking about the 8-bit representation, it's the same story. Okay, it's the same story. So we have the 8 bits. Okay, we have the 8 bits. The first bit is obviously allocated for, the sign of the decimal number. Okay, so in positive, okay, in positive values, it's the same. Okay, it is the same. You just have to find the binary number and you have to fill out the values. For negative numbers, it's a little bit different. Okay, first of all, let's focus on positive numbers. Let's say we have to write down the value 99 to the base 10. Well, 99 to the base 10 is equals to 64, 96, and no 16, no 8, no 4, and that is 1, that is 2. So, yeah, this is the binary equivalent for 99 to the base 10. So, since this is a positive number, you'll write down the 0 first, since the first bit is for sign, and the other 7 bits are for the magnitude. So, we have 1, 1, 0, 0, 0, 1, 1. Okay, so this is the two's complement form as well as the one's complement form or the sign magnitude form of a positive number. Positive numbers are not complex. It's the same for all 3 representations. But in two's complement, when you are converting to a negative number, okay, when you are converting to a negative number, what you have to do is you have 2 steps to follow. Okay, you have 2 steps to follow. Okay, first of all, you have to find the ones complement. Okay, if you have to write down this is the 99 to the base 10 positive 99 to the base 10. Okay, this is the 2's complement for positive 99 to the base 10. Okay, to find the negative 99 to the base 10, what you have to do is first of all there is an intermediate step. Okay, you have to convert this to ones complement form. So if you convert it to ones complement form, you will have 1, 0, 0, 1, 1, 1, 0, 0. So this is the ones complement of, the negative 99. Okay, this is negative 99 to the base 10, but this is ones complement form. It's in the ones complement form. It has not reached the two's complement form yet. Okay, so to find the two's complement, what you have to do is you just have to add 1 to this. Okay, the final step, you have to add 1 to this. So if you add 1 to this, you'll get negative 99 to the base 10, which will be equals to 1, 0, 0, 1, 1, 1, 0, 1. Okay, so this is what you have to do when you are converting to negative numbers. When you are converting to negative numbers. So I hope you understood the basic idea. Let's do some practice questions to come up with the good foundation. Okay, so let's say we have a simple number like 5. Okay, let's say we have a simple number like 5. Well, we know positive 5 to the base 10 can be represented as 101 to the base 2. Okay, so what's the two's complement form of positive 5 to the base 10? Well, the first digit is 0. Why? This is a positive number. And we need 7 more bits, but we only have 3 bits to represent. So we will just fill up the other 4 bits with 0. Then we'll write down 1, 0, 1. So this is the positive 5, 2's complement, 1's complement, signed imaginary. But in this case, let's just say 2's complement form. Okay. This is the 2's complement representation of positive 5. Now we have to find the 1's complement of negative 5. So negative 5, 1's complement. Okay, that's what we are going to find. Okay, we are going to find 1's complement negative of positive 5. So it is negative 5. So it will be flipping the bits. So 1, 1, 1, 1, 1, 0, 1, 0. So this is negative 5, 1's complement. So what will be the negative 5, 2's complement? What will be the negative 5, 2's complement? You have to add 1 bit. Okay, you have to add 1 bit. That's all you have to do. So if you add 1 to this number or this representation, you will get 0, 1. That's it. So positive 5 is this in 2's complement, and negative 5 is this in 2's complement. Okay, let's do another number. Let's keep practicing. Yeah. So let's say we have a number like, maybe 79. 79 is easy. Let's say 190. We have to convert. We have to find negative 190. So we start with positive 190. So 119 to the base 10 can be given as 64, 96, 112, and we don't have 8 here. So there will be other 4, 2, and 1 to the base 2. Okay. So this is 119 to the base 10. Cool. Now, what you have to do? Well, that's a good question. So what you have to do is you have to write this down in the 2's complement form. Since this is a positive number, you'll write down 0 here. Then you will continue with the other number. Okay. So this is the positive 190 to the base 10 2's complement form. Okay, 2's complement. Now we can find negative 190 to the base 10 1's complement form. So that will be flipping the bits 1 0 0 0 1 0 0 0. That's it. This is negative 119 to the base 10. Now it's in 1's complement form. Now you have to find the 2's complement form. So negative 119 to the base 10 in 2's complement can be given as by adding 1 to this. So if you add 1 to this, what will you get? You'll get 1 0 0 0 1 0 0 1. That's it. That's all you have to do. Okay. So what is the interesting part about this? Well, here you can actually find the range. Okay. So in sign magnitude, it was straightforward. Yeah, it was straightforward. If you have n number of bits, okay, we have in sign magnitude, if you have n number of bits for representation, okay, the maximum positive number that you can have is actually 2 to the power n minus 1 minus 1, okay, positive 2 to the power n minus 1 minus 1 to negative 2 to the power n minus 1 to minus 1. Okay, this was the range. If you have n number of bits to represent a decimal number in sign magnitude system, this was the thing. Okay, so what do I mean by this? Well, if you have 8 bits, okay, the positive number, the maximum number that you can represent is 2 to the power 7 minus 1, which is equals to 127. And in negative, it will be negative 127. The minimum number will be negative 127. That's it. Okay. If you have 16 bits, well, it changes because 2 to the power 15 minus 1, because n minus 1, the power is n minus 1. So it will be equals to 32,763. So since we are subtracting 1, it will be 32,767. So nearly 32k. Okay. And in negative, it will be negative 32,767. That's it. Okay. So this is in sign magnitude system. It is the same for 1's complement also. It's the same for 1's complement also. In 1's complement also, if you have n number of bits, that's the same case. Okay. If you have 8 bits, you can represent from 127 to negative 127. If you have 16 bits, you can represent from 32,767 to negative 32,677. Okay. But when it comes to 2's complement, the story is different. When it comes to 2's complement, the story is different. The story is different because 2's complement only has one zero. Okay, in sign magnitude, okay, in sign magnitude we had two zeros. Okay, positive zero was 0, 0, 0, 0, 0, 0, 0, 0. Negative zero was 0, sorry, not 0, since negative it's 1, 1, 0, 0, 0, 0, 0, 0, and 0. And in one's complement, okay, in one's complement, the positive zero was, well, it's the same as sign magnitude 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Negative zero was 1, 1, 1, 1, 1, 1, 1, 1. Okay, but in two's complement, okay, in two's complement, we only have one zero, and that zero is 0, 0, 0, 0, 0, 0, 0, 0. There is no negative zero. Only one zero is present in two's complement. That's why it's widely used in every application. It's very efficient. So when compared to sign magnitude and ones complement system, this is very efficient. So that's why it is used in multiple computer science cases. Actually, that's why we use it, and it's low cost. Okay, and it's since it's efficient, it's also high speed hardware. Okay, the arithmetic operations are really fast when you use two's complement, and yeah, this is what we use nowadays. Even in Python, when you are focusing on the shift and sorry, not shift. We have this bitwise not operation. Okay, bitwise not operation. In bitwise not operation, we actually need two's complement. Okay, I'll explain it in the future video. But now let's focus on two's complement. So, what is the range for two's complement? Well, for the range of two's complement, if you have n number of bits, okay, if you have n number of bits, definitely the positive one doesn't change. Okay, the positive one obviously doesn't change because it is 2 to the power n minus 1. Okay, 2 to the power n minus 1 minus 1. Okay, so it is same. For the positive number, it will be 2 to the power n minus 1 minus 1. Okay, but negative number, you can actually have 2 to the power n minus 1. Okay. So if you have 8 bits, the thing is you'll have 2 to the power 7 minus 1. That will be the maximum number, which is 127. But in negative, you can represent up to negative 128. And similarly, okay, and similarly, and in 2 to the power, so if you have 16 bits, you will have 2 to the power 15 minus 1, which is equals to 32,767. But you can represent until negative 32,768. Okay, so that's the only important thing that you have to take away theory-wise. Okay, that's what you have to take into account when you are working in the theory part of two's complement. Okay, so we have talked about two important things. Okay, one was how you can find the two's complement of decimal number, and now we have discussed about the range. Okay, so in the next video, the second part of two's complement, I'll teach you how you can convert from the two's complement form to a decimal number. Okay, two's complement form to decimal number, and we are also going to learn about how we can perform decimal additions and subtraction by using two's complement method. Okay, but today in this case you will have a small doubt. Okay, how can we represent negative 128? I'm gonna cover that now itself. Okay, so how can we represent negative 128 in two's complement system? So that's a good question because I told you when I started this, I told you the first um, bit is given for sign. Okay, how can I represent negative 128? Normal question. For this one, okay, for this one, when you're starting from positive, you will have an issue. You will definitely meet with an issue. Okay, so the problem is you can't come up with 120 because even if you fill all these bits with 1, the maximum you're going to get is 127 to the base 10. Okay, the maximum you're going to get is 127 to the base 10. So how is it going to work? Yeah, that's the question that we have. The thing is, for only 128, the highest number, okay, since we are finding negative 128, for the highest number only, we are going to use 1, 0, 0, 0, 0, 0, 0, 0. This is how you will represent 128, right? Because I know this is for representing the, this is for representing the sign, okay? But for 128, if you want to find out the negative 128, you have to forget that rule. Okay, there are exceptions, obviously. So you have to forget that rule. So is it 128 to the base 10 in 2's complement? No. Okay, no. This is not 128 in 2's complement. No, it's not true. Because we can't find 128 because the range doesn't allow that. Okay, so you have to start from here. Think of it like it's a virtual thing. It doesn't really exist, but you use it for your benefit. It's like a pseudo thing. Okay, it doesn't exist. So now what you have to do is the other steps are straightforward. Okay, the other steps are straightforward. What you have to do is, first of all, you have to convert this to ones complement. So it will be 0, 1, 1, 1, 1, 1, 1, 1. And you have to add 1 to this, and you will find the negative 128 in 2's complement. Okay, it's not magic. Okay, it's not magic, but we just follow some exceptions. That's all. So if you add 1, you will get 1, 0, 0, 0, 0, 0, 0. Okay, so how can we verify this? Okay, that's what I'm going to teach you in tomorrow's video. So stay tuned.
Thanks for watching the 15th video in our number system series. If you found this tutorial on ones complement and two's complement representation helpful, don't forget to like, share and subscribe for more lessons. Hit the bell icon to stay updated with our latest videos, check out the full playlist to master number systems and follow us on Instagram. I'll see you in the next video. Until then, keep learning and stay curious. Bye bye.